The topic for this lesson is the time constant of an inductive resistive circuit. We will first discuss current buildup in an inductor. The circuit shown consists of an inductance L, a resistance R, a voltage source E, and a switch. The switch is open before T0, and the value of the current is 0. At T0, the switch is closed and current begins to flow. The current increases gradually from 0 to a final steady state value. When the current reaches this value, the voltage across the inductance becomes 0 and all the applied voltages across the resistor. The final value of current is defined by Ohm's law and is E divided by R. The graph shown indicates the variation of the current in the circuit as a function of time. The time constant of an LR circuit is the time it would take the current to rise to its steady state value if it were to continue to rise at its initial rate of change for the whole time interval. The time constant is expressed by the Greek letter tau and is expressed as the ratio L to R, or tau is equal L divided by R. If the inductance is large, it will store more energy, which means that it will take longer for the current to build up. Thus, the time constant is proportional to L. From the graph shown, we observe that the approximate time to reach the steady state value is 5 time constants. Let's look at an example. In the circuit shown, calculate the time constant, the final steady state current, the approximate time to reach the steady state value, and the energy stored in the inductor at the steady state condition. The time constant is given by L divided by R, or 1.5 henries divided by 30 ohms, which equals 50 milliseconds. The final current in the inductor is given by E divided by R, or 200 divided by 30, which equals 6.67 amps. The approximate time to reach the steady state value is 5 time constants, or 5 times 50, or 250 milliseconds. The energy stored in the inductor in the steady state is W is equal to 1/2 L times I squared, or 1/2 times 1.5 times 6.67 squared, or 33.4 joules. We will now turn our discussion to decay of current in an inductor. In the circuit shown, the switch is initially in position 1 until T0 and is then moved to position 2. Prior to T0, the current in the inductor has built up to a steady state value of E divided by R. R2 becomes part of the circuit only after T0. When the switch is moved to position 2, the voltage source and R1 are no longer part of the circuit, and a new path is established consisting of L and R2 as shown. The energy stored in the inductor as a result of the current in it at T0 will now be dissipated through R2. The current gradually decays from its initial value of E divided by R to a final value of 0. All the energy that has been stored in the inductor at T0 has now been dissipated by the resistor. The decay curve is shown in the graph. The time constant governing the current decay is equal to L divided by R2. Notice that it takes approximately 5 time constants to decay to 0. This is an exponential decay curve, whereas the current buildup curve is an exponential growth curve. Let's look at an example. A 20 millihenry inductor has an additional current of 4 amps. It is connected to a 60 ohm resistor that causes the current to decay to 0. Calculate the time constant of the circuit and determine the current at the end of the 3 time constants. The time constant of the circuit is given by tau equals L divided by R, or 20 millihenries divided by 60 ohms, which is equal to 0.3 milliseconds. From the universal exponential decay curve, the current at the end of 3 time constants is 3 times 0.3, or 0.9, has decayed to 13.5% minus 8.5%, or approximately 5% of its original value. The table shown gives a tabulation of percentage growth or decay and the ratio of L divided by R time.